to my tissues, which would be picked up by this autonomic nervous system, which would cause sympathetic fibers to fire, which terminate in these nodes. Does that make sense?
Mm-hmm. So the pacemaker would affect the SA node, then in turn affecting the AB node.
Yes.
To meet the demand.
Yes. So if it becomes a problem where there is something wrong and you finally are like, you know, I just don't feel as good, my heart's not beating good, I feel short of breath, whatever the case may be, okay, finally go to the hospital, finally get checked, they finally determine, okay, well, the SA node's not firing like it should. Put in the pacemaker will help it. Okay? There's tons of things now, I think. They've got like the pacemaker, they've got the defibrillator.
Yeah, they have the ICD, they have a, if you can't have the ICD, they have a thing called a life vest that you wear, which doesn't sound very fun at all, because, you know, you get zapped.
Whoa, life vest, as
Like
in it shocks you from the outside in?
Yeah, they have to keep it. I have a patient who has like a congenital thing that like I think a good chunk of his family died from. And he came in, and he didn't want to believe. He still doesn't. He kind of denies the fact that he's like sick. He's like, no, I'm just here because I wasn't feeling well. She's like, no, your fiber rate's like 10%. You're like chest. You're like, you know, heart cath was like terrible. But he was just like, no, I'm fine.
That sounds painful.
Yeah, so he just wears like a life vest.
Okay, yeah. So anything that would stay consistent at like 40 beats per minute. The reason that this becomes such an issue, all right, we are not getting blood flow to the tissues. When we don't get blood flow to the tissues of the body, we're not getting nutrients to the cells, we're not getting rid of waste. The tissues can begin to die, all right? That's why they have to address this issue. If not, death will ensue. So the SA node, as long as that's working, you're good. Anything else that would cause the beating of the heart is considered an ectopic focus. And you'll see that. You'll see that on lab reports, and you'll see that on patient notes. They had an ectopic foci. They had an ectopic focus. They're letting you know that something with that beating of the heart did not work. Our SA node, do you guys remember resting membrane potential? What was that? Hopefully you talked about it in relationship to skeletal muscle and the nerves. Do you remember anything about an RMP?
Isn't it kind of like just similar to the tone we were talking about, like the ability for the ions to travel?
It does. It is based on inflow and outflow of those ions. This will probably trigger your memory. And then you'll be like, yeah, I remember that.
It's like that.
Yeah, sure.
Energy that shows like that's right.
See, are y'all all going, oh, yeah, remember that, okay? But what's the importance of this?
It's actually ready to happen.
It's letting us know information about an action potential. Because you have that in skeletal muscle, you have it in nerve, we're still in muscle, okay? So it would stand to reason it's present, okay? Now, the fact that it means membrane, what does that tell us? One thing that I did at the very beginning of our class, I talked about a cell, I talked about that plasma membrane, and what is it that happens across the membrane of a cell? You just told me.
What, the passing of ions?
The passing of ions. Meaning, if they cross, most of the time we're going to get an action potential. We need sodium-potassium pumps to balance it back out and let it go to rest. Do you remember that with a skeletal muscle? You had the nerve meet that skeletal muscle. At the synapse, acetylcholine crossed, and it started the action potential because you had ligand-gated, voltage-gated, sodium-potassium. Does everybody remember that? We're still looking at cells. We're still looking at membranes. We are still looking at movement of ions. And we test it by way of that EKG. So now we're going to see that we have an action potential based on movement of these ions. Okay? Resting membrane potential. When you looked at skeletal muscle, okay, you would get to see it return to rest, and it could stay there if the muscle wasn't active. With a nerve, you could see that it could actually dip a little deeper before going to rest, okay? And once again, the nerve could kind of stay rested if it wasn't actually sending a signal. Now, we have the situation where we're talking about an organ that is going to go through a cardiac cycle roughly every 0.8 seconds. We look at that roughly 75 beats per minute. We're looking at roughly 0.8 seconds. For a complete contraction, relaxation, recovery, and starting all over again. So once again, we're going to have the graph. Okay, do you guys remember how you started out at whatever that resting membrane potential was? Like for example, -35. If, say for example, it was skeletal muscle, it received the impulse from the nerve, and then it reached threshold. Does anybody remember that term? Okay. If it reached threshold, that muscle contracted no matter what. Okay. In skeletal muscle, we could also have where it would be a sustained contraction. Do you guys remember that before it could go to rest? Now, in cardiac muscle, that 0.8 seconds, in that 0.8 seconds, we need it to go from resting to contraction, back to the relaxation, to recovery, and start all over again. Because if we have it stay sustained, hold up. Do I need that when that heart beats, and it goes whoosh, and to just no, I can't have that in my heart. I don't want that in my heart. It needs to go. Do this every 0.8 seconds. Okay? So now, let me think about this for a second. Does that seem like enough time for one of those little tiny heart muscles to have rest, contract, relax, start all over again? My brain, it doesn't. I can't think those numbers. Okay? Now, our SA node, because once again, modified cells, okay? It does not have a stable resting membrane potential. So what that tells me on this chart right here, where I would think of a resting membrane potential being, it would not have a definite number associated. That number would be going up, down, up, down, up, down, up, down, up, down. Okay? It's not stable, which, based on how quickly it has to work, that's understandable. Okay? It shows us that it does have, which side is polarization, depolarization? Do you happen to remember? Okay, so polarization, depolarization. Okay, so it shows gradual depolarization. So it would almost be like this side's going woo, 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 before it gets back to rest, where it's going like this. Okay? It would not be definite numbers that are present, if that makes sense. So basically, we're getting a slow flow sodium based on what we have learned up to this point. Skeletal muscle, nerve. What was a major ion? Sodium. Because why? Sodium is higher in content outside of a cell. When it flows into a cell, it affects the number. Right now, my number, negative. But if I have an influx of sodium, does sodium have the positive or negative charge? Positive. That is what makes this move up. Does that make sense? Then, because I cannot keep a cell more positive on the inside than the outside, I finally reach a point where it can't take any more, and it will begin to move sodium out. The sodium-potassium pump. Because I got to bring it back to my rest. So for our SA node, we have the slow flow of sodium. It's almost like you have sodium just continuously coming in, so that this is continuously going boom, 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 and go up and go woo, 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 back down to where I've got more sodium, and I go boom, 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 and up, 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 keeping my SA node fired. It doesn't let it go into complete rest. What would happen if that SA node